All right, guys, we're going to talk about polynomial functions today. All right, standard form for a polynomial function is just a straight up polynomial with coefficients and exponents on the variable. Normally our variable is going to be x. So nth degree, whatever the highest exponent is the degree we're talking about there. The a sub n, those are just the coefficients, the numbers that are in front of the variables there, just the notation that they're using. But it's in descending order. That's what we're indicating here, from n to n minus 1. The next one to be n minus 2. Take your degree, your exponents, greatest to least, and that's standard form for a polynomial. Nothing that you haven't seen before. A sub n, those are real numbers, cannot be complex numbers as coefficients. The n's, exponents, they're non-negative integers. And what's it mean to be an integer? What are integers not? Maybe that's an easier question to answer. Give me an example of something that's not an integer. Zero is an integer. True. But not what I'm going for. I'm talking about numbers. Even has nothing to do with it. Integers are not fractions. Okay, it's non-negative integers, 0, 1, 2, 3, 4. You know, those numbers are what we're dealing with here, not fractions. You cannot have fraction exponents. That's what I'm trying to tell you here. Integers, you should know what that is. You're big enough to know that. My dad would say. To be a polynomial, there are certain conditions that have to be met to be classified as a polynomial. One of those is no negative or non-integer exponents. Okay. Non-integer, meaning they are fractions or decimals or something. It's not an integer. Negative exponents, that introduces the idea of dividing by a variable, and we can't do that. Okay, no negative exponents because that puts the variable in the denominator once you make that a positive exponent, and you can't have that to be a polynomial. We'll get into that later on in chapter 5 when we talk about rational expressions. That's when the x is in the denominator. All right, so no rational expressions with variables in the denominator. Doesn't mean it can't be a rational expression, just means it can't have variables in the bottom. It can be a fraction as a coefficient, or you could write, this is x squared plus 4x over 3. That's a rational expression, but it doesn't have a variable in the denominator, so that makes it legal. If you just did this, then it's not a polynomial anymore. Okay, so that's what that particular statement means. Okay, when we talk about a polynomial, one of the good things about polynomials is they're very much related to quadratics, that the domain negative infinity to positive infinity. All real numbers for the domain of a polynomial. And range is dependent upon what polynomial we have, maximum, minimum values, absolute maxes and mins, and depending on the degree of that polynomial, whether you would even have a minimum, absolute minimum or maximum. So the degree of a polynomial is its highest exponent. In standard form. Highest exponent when it's in standard form. So then we're looking at the exponents on the x's when that's happening, and the degree tells us a lot of things that we're going to discuss as we go along when we're dealing with polynomials. So this is very much the same thing we did in Algebra 2. There's not much difference in this and what we did in Algebra 2. It's just very much the same thing. Okay. All right, so let's play the next big game show. Is this polynomial? And if so, state the degree. So it's kind of a long title for a game show. We'll probably have to change that when we make it public, but you can write the jingle for the start of it. Yeah. No. All right, so here we have f of x is equal to 3x to the fourth power minus 5x cubed plus 2x squared plus 6x minus 7. We want to know, is that a polynomial? So we check the conditions that have to be met to be a polynomial. Those conditions are that you cannot have negative exponents or exponents that are not not integers. So looking for fraction exponents. If they're there, then we know it's not a polynomial. If they're negative exponents, we know it's not a polynomial. Those are the things that make it not a polynomial. We have 4, 3, 2, 1, and then x to the 0. So that none of those are negative. None of those are fractions. So it meets the criteria to be a polynomial. So the answer to that is yes. Its degree would be what? 4. And that tells us some things about that fourth degree. The even degreed polynomials tend to shape themselves somewhat like a quadratic in that both ends go the same direction. So if it's fourth power, you know, and this one has a leading coefficient of 3, so it's positive, so it opens up. The difference in it and a quadratic is as the degree gets higher here, if it's even, it could have like humps in the middle. That's the difference. But as far as end behavior goes, that degree tells us, hey, if it's even degree, both ends are going the same direction. If it's positive in the front, both ends are going up. If it's negative in the front, both ends are going down, just like a quadratic does. Okay, so kind of tying some of those things together as we go this year to try to help that issue. I don't understand why it's an issue, but it is. So 6x to the 5th minus 5 square root x. So, is that a polynomial? And if so, state the degree. It's better catch to it. But looking for negative exponents or exponents that are not integers. This one has a square root in it. Is that, what's the exponent that goes with square root? 2. The index is 2. It's really like a 2 right there, but the exponent that goes with it is 1/2. That's the exponent. Remember that? So this is not a polynomial because of that. Doesn't mean it's not a function, just means it's not a polynomial function. So we don't get some of the things that we're going to learn about polynomials that come along with it. No, it means x to the 1/2 power. That's what that means. And a cubed root means x to the 1/3 power. Whatever the index is on the root is the denominator of your fraction. Exponent. That's how that works. All right, let's look at C. H of x is 2x cubed, parentheses, x plus 4 squared. A little bigger polynomial, but it looks small, but it's bigger. Is it a polynomial? Do we see any fraction or negative exponents? No. So it passes that. It's not a rational expression, so that definitely works. So this is a yes. And the tougher question for this one is, what's the degree? Say that again. All right, okay, so we got to work it out somewhat to get the degree. We just need to know what's the highest exponent going to be. Not saying we got to multiply this out all the way and get the big long polynomial. Say that again. Why is it going to be 5? Explain to us how you got there.
I wouldn't get it.
You multiplied it all the way out. That's one way to get there.
You can go because you're gonna have to square it, which means that x is gonna be multiplied by itself, so it's gonna x squared and times x to the third. So
There you go. Okay, so that's the shortcut to it. We're just looking for the highest one. If we're asked for the degree, then so we know when we square this binomial, this is going to become x squared, and we would distribute this, and x cubed times x squared is going to be the 5th degree. Now you could multiply if you're going to do something else with it. You'd probably multiply it all the way out if you were going to do some other things with that. But just to get the degree, we're going to just get the leading term there. You can take that shortcut to get the degree out of that, which is helpful sometimes. F of x is equal to cube root of x plus x to the -5. Is that a polynomial? That's a definite big no on that one. It's got 2 things wrong with it, right? This x to the cube root of x is x to the 1/3 power. And then how do y'all remember how to fix a negative exponent? Yeah, that's right. Put it under 1. And so there we have not only a fraction exponent that's not an integer, we also have a rational expression that has an x in the denominator. That's where that comes in. So one of those is enough to make it not a polynomial. This one happened to have both of those, but one can do enough. So this is not a polynomial. Okay. One more in the game of polynomials here. F of x is equal to 1/5 x to the 8th parentheses x squared minus 5 to the 3rd power. So this one's a little tougher because it's not as small a thing, and multiplying it out completely would take a great deal of time to do this one. All right, so this is where that shortcut for the leading coefficient, leading term is helpful. Okay, so this one is a polynomial. What's its degree? 14. Yeah, because you cube x squared, it's going to give us x to the 6th, and then times x to the 8th, and then it's going to 14 there. And that's all we need to know about that. As far as when they're just asking for the degree, we're multiplying out the leading term. Now, don't make that mistake of, if you do have to multiply this out, just cubing x squared and cubing 5. This does not multiply out to be x to the 6th minus 125. It's got a whole lot of other stuff in the middle. Okay, so don't make that mistake if you do have to multiply it out, which we will later in the lesson today. So, all right, now let's make ourselves a little chart here, talking about different polynomials kind of generic ones and what they're called and what they look like based on that information. So we're going to look at the degree is our first column. And then we're going to look at what that looks like, what the form of the equation is. And we'll name that polynomial like Bill, Jim, something like that. And what the graph looks like. Just a small sketch of the graph there on the right-hand column. So degree, we have polynomials that can have no degree. It's the most forgotten polynomial in the world. It has no degree. It is f of x equals 0. Its name is the zero function. That's just what it's called, the zero function. Zero, if 0 is the only thing in the polynomial, it doesn't have a degree. And the graph is, I'm just going to sketch a small coordinate plane here. And then it lies right on the x-axis. Is what the graph of that looks like. We should know that anyway. Y equals 0. It's going to be that. But that has no degree. That is slightly different than a polynomial of 0 degree that looks like this. F of x is equal to a sub 0. Remember when we did the standard form at the beginning, the a sub n's, they're just real numbers. So this is any other number other than 0. So it could be -6. It could be, 125. It doesn't really matter what number this is. It's just a number. And that's the, does anybody remember what that's called? Back from chapter 3 or in the library of functions. When we were doing the piecewise. Constant function. And in general, it's just a horizontal line somewhere besides the x-axis. So it could be, if it's a positive number, it's a horizontal line up there. If it's a negative number, whatever y value it is, just go there and make a horizontal line. So that's the constant function. It has a degree of 0. So if it's just a number, that degree is 0. And then degree 1, f of x is equal to a sub 1 x plus a sub 0. Back in junior high, we did this. All right, there it goes. Mx plus b. So this, what's the name of this function? What's it called? That in blue there is a hint. The slope-intercept form of a what? Line. It's a linear function. So it's called a linear function, and we know it looks like a line that's not horizontal, slanted in some way, shape, or form. So there's one with a positive slope. We know a negative slope and all that stuff. So that's a degree 1 polynomial. We've been dealing with that for a long time, since junior high math. Degree 1 polynomials, we know a lot about those. They got slope, they got a y-intercept. We know what they look like on a graph. We're very experienced with degree 1 polynomials. We just never called them that in 6 years of math here. So, but that's what they are. So degree 2 polynomials. We just finished a couple of sections in a chapter about degree 2 polynomials. F of x, a sub 2 x squared, a sub 1x plus a sub 0. What's the name of that? Quadratic. We know what shape does that make in the graph? Parabola. There's one that opens up, has a vertex that's somewhere down below the x-axis there. It doesn't really matter. It's just a generic idea that it's a parabola. But notice that, the the degree of that is 2. It's an even one. Notice the two ends are going the same direction. What direction they go is dependent upon a in the front of x squared. If it's positive, it opens up. If it's negative, it opens down. That same idea is going to carry over as we go a little higher degree. So if we go to degree 3, f of x is equal to a to the sub 3, x to the third, a sub 2x squared, a sub 1x, a sub 0. Third power is also called what? Cubic. Yeah. Cubic functions are very similar to linear functions because their degree is odd. So they do a lot of the same things, but instead of making a straight line, they make a picture something like that. Move it up, down, depending on what numbers are in the coefficients there, where it's at, and how big those curves are in there. But notice the degree's odd on the linear function, and the ends are going in opposite directions. Here, the degree's odd, the ends are going in opposite directions. If you can get that general concept down, it's going to help you a lot as we build up to doing more stuff with the graphs of polynomials. If we go to degree 4, f of x is equal to a sub 4 x to the fourth. And go all the way down to a sub 0. We normally just call this a 4th degree polynomial. It does have a name, and it's very seldom used. Quartic is what it is sometimes called, but it's very seldom that you will hear anyone in modern mathematics call it that. Some of the old guys might call it that, but most people that are up to date on nomenclature in math, they don't say quartic anymore. It's just 4th degree. And if we go higher, 5th degree, we just say 5th degree polynomial. Technically, the old folks would call it quintic polynomial, but we just don't do that anymore. We just, anything higher than cubic, we just name it by the number of degree it is. So that's going on. So the graph of that, again, it's an even degree, so it's similar to a parabola in that the ends are going to go both the same direction. So if the leading coefficient a sub 4 here is positive, if they're both going to go up. If it's negative, they're both going to go down. The difference would be the number and size of the changes in direction in between the ends there. So odd degrees, if you can remember what a line does, it can help you understand the end behavior of odd degree polynomials. Even degrees, you have a lot of knowledge about quadratics. They follow suit with quadratics with that. So that can help when we talk about end degree a good bit. All right, so let's look at just a simple graph using the graphing calculator of a polynomial. So all right. So before we graph it, let's look at information we know about this polynomial already. I'm telling you it's a polynomial. We know it's a polynomial because we don't see any fraction exponents or negative exponents or x's in the denominator. So we know it's a polynomial. What do we know the degree of that polynomial is? It's 4th. It's 4th degree. So what do we know about its graph? just based on the chart we just made. It's going to look kind of like a parabola. It's got both ends going up or down for this one. Why up? That's right. Yeah, because A's not going to be negative. We got this positive 1/2 out here in the front. There's nothing in front of any of these that would change that sign. So we're going to have a positive. We know it's going to open upward. We know there's a lot of stuff going on in between there. Let's look at the graph of that and kind of see what's happening there. So parentheses, or excuse me, 1/2 parentheses. I don't even know what it was. X minus 1, X plus 3. Close parentheses squared, parentheses, X minus 4. Yep, right. Which one was it? Okay, thank you. All right, so I'm going to zoom out so we can see a little bit more of the picture. Zoom out from the center. We see both ends going up. It's not as similar to a parabola as we would, kind of in a simplistic way hope it would be. But both ends go the same direction. We see the humps in the middle. That's going on. Notice where it's crossing the x-axis. Where is it crossing the x-axis? Or touching it, even. Yeah, so if I zoom back in, or zoom 6, get back there to the normal graph. Eventually. Is it doing the same thing? Okay.
While I'm waiting on that, can I ask a question?
Yeah.
Yeah, I should already know this, but
Okay.
how do we get the highest one that was for?
If we were to multiply it all out, the leading terms, you have plain x from the first parenthesis. The second parenthesis is squared, right? Mm-hmm. So when we square that, the leading term is going to be x squared in it. So x times x squared is x cubed. And then we had that x minus 4 on the end. So x times x cubed gets us the extra 4. Good question. And it's still not working. So. I don't have that option here to just turn it off, close it. Maybe I won't. I don't know. Yep. Whoa, that was weird. Close. Stop. The robot revolt. All right, so that didn't work.
She said very loud.
Yeah. I'm just up here trying to not be offended. Yeah, it is. Go ahead. All right, just be that way. It's not you, it's me.
Everything you want to hear on Valentine's.
Yeah, exactly. That's exactly what I was saying. It's not you, it's me.
It's gonna be like eating dinner later. His wife's gonna be like, "What's wrong?" It's like,
Now, if I can make it home today, I'm good. Jeez. What is the deal?
oh yeah.
I'll just open another one. How about that? All right, back at it. So the graph crosses the x-axis at 1 and then touches the x-axis at -3 and then crosses the x-axis again at +4. We see that happening there. Notice the numbers that are in our factors. That's That's where the numbers are coming from. How of that? Still going. I'm just giving it more things to do. It's probably not helping at all. All right. All right, so we see this graph touching the x-axis here at 3, crossing the x-axis at 1 and 4. What's the difference in the factors that were in the problem at, for the factor that said x plus 3 and the factors that said x minus 1 and x plus 4? True. That's one thing. Good. What's the other thing that's different? That one of them squared, right? Which one is squared? And notice what's happening on the graph at x plus 3 or at x equals negative 3. It's just bouncing off the x-axis there. That we saw that in Algebra 2, or should have, that a multiplicity of an even amount touches the x-axis or bounces off of it. A multiplicity of odd degree, or a factor that has an odd degree, has it crosses the x-axis. So that's going to help us as we build up later on. So looking at that graph, good deal. Let's talk about a transformation. Describe. This is coming up again. We talked about this in chapter 3. Describe the transformations on f of x equals x cubed. So the parent function here is the cubic function f of x equals x cubed. And our one we're deciding what's happening is this. 2 parentheses x plus 1 cubed minus 4. So what transformations are happening without graphing this? What transformations are happening? Down 4. Left or right? Left 1. What else? Vertical stretch or compression? Stretch. Factor of 2 on that stretch. Why is it a stretch and not a compression? Above 1. If this is a bigger number here, then it's a stretch. If it's a smaller number, it's a vertical compression. If that 2 were on the inside with the x there, what would it do? Horizontal compression. So that we remind ourselves of those rules are always handy. Okay. Look at 8. Another describe problem, but not of transformations. Describe the zeros of the polynomial f of x equals 5 parentheses x minus 2 parentheses x plus 4 squared parentheses 2x minus 3 cubed. Describe what's going on with the zeros. What are zeros of a polynomial? What's another name for that? A synonym for that?
Amanda Nowicki is looking for a job right now.
Okay. All right. Now, what another name for zeros? You should know this.
I'm sorry, we need that Thompson too. Thanks.
Okay. All right. Y'all go when you gotta go. zeros, x-intercepts, same thing. Zeros, x-intercepts, roots is another name for that. Roots is usually like the older school name for that, but it's still used. Zeros, roots, x-intercepts, those are all the same things. Solutions to a polynomial, they may even call them that. But it's where is the polynomial equal to 0 at? And if you take a polynomial and you set it equal to 0, you're replacing y with 0. So that means, everywhere there's an x and y is 0, then it's on the x-axis. So that's an x-intercept. So zeros are x-intercepts. Zeros are roots. Zeros are solutions to a polynomial. That's the idea there. So without graphing it, we're going to graph it too, but without graphing it, what's going on here? Okay, so it's going to, what's it doing when I say x minus 2 equals 0, I get x equals 2, right? What's happening there? Okay, cross x-axis. And then when I said x plus 4 equal to 0, I get x equals negative 4. And it also has a multiplicity of 2. And because it has a multiplicity of 2, it touches the x-axis. Doesn't cross it, touches. Bounces off is how I usually look at it when we look at the graph. If it's got an even multiplicity, it's going to either come down, hit the x-axis and bounce back off, or it could come up, hit the x-axis and bounce back down. Okay. So it touches the x-axis if it's got an even multiplicity. And then the 2x minus 3, if I set that factor equal to 0, I'm going to get x equals 3 over 2. And that 0 has a multiplicity of 3. So that's an odd multiplicity. So that means it crosses the x-axis. Okay, so even multiplicities bounce off or touch the x-axis. Odd multiplicities cross the x-axis. Keep that in mind as we go forward from here throughout the chapter. So be aware of that. All right. If we graph that, let's see if it'll do it without screwing up this time. X minus 2, parentheses, x plus 4 squared. Parentheses, 2x minus 3. Thanks, man. Have a good trip. Seth, you need to go? All right. And then we graph that. We should see those things. We'll see some weird stuff happening there. We don't see it crossing or crossing the x-axis. Well, we do see it crossing it. Where should it be touching it? At negative 4. Why do we not see that? We know it's there, but the graph doesn't show it. What happens if I zoom in at negative 4? Whoops. Zoom. I'm going to zoom in. I'm going to scoot over here toward negative 4. Somewhere close to that. See if I can zoom into that spot and see what's happening. Because I know there should be something, happening there. Huh.
Well,
let's do it again. Oh, wait. There's a hint of a line there. We know it's, hey, here's the thing, guys. So many people I saw in Algebra 2 relied only on the calculator to do this stuff. Yeah. It does not work. Because you would miss it because you wouldn't have the 0 at negative 4 because, especially if it was one that was multiplied out and not written in factored form for you, right? This is where you've got to know how to do this without the calculator. The calculator is a handy tool, but it doesn't do everything for you. You got to have that brain that's between your ears. God gave you that for a reason. Notice how it's, as the more I zoom in, the more it's looking like that loop that's going to touch and bounce back up. If I zoom in again, you'll see, it's even more. The resolution is, it's such a skinny part of the graph that it can't draw both lines, and it comes down and bounces, so it can't even draw. It's so skinny that it can't draw. So see, we see it really clearly there. If that's what's going on. Okay, so that's my lesson for the day. If you did this all with a calculator in Algebra 2, well, you stop. So my dad would say, "Well, stop doing that, and start doing it the right way." So, not that the calculator is a bad thing. I'm as much pro technology as anybody is, but it's got its place, and you got to have some knowledge to know how to use it right. So that's an important thing. All right, next thing in this section, we got just a few minutes left for we're going to call a meeting. So turning points. This is the easiest thing that we'll do the whole chapter. Turning points means those places where the graph changes direction. Okay, turning points, polynomials of degree n have at most n minus 1 turning points. That means they have n minus 1 changes in direction. Okay, think about a quadratic. Its degree is 2, right? And if it's opening up, it comes down to the vertex and then changes directions. 2 minus 1 is 1. That's changing direction. 1 turning point out of that. A cubic does this, so we know that, it's got n minus 1 to be 3 minus 1 is 2 turning points where it's changing directions out of that. At most, it can have that number of turning points. That doesn't mean it will have that many, but it could have that many. Okay, so what we're going to find in this particular section is what's the maximum number of turning points a polynomial could have. So find the maximum number of turning points for the given polynomial. The easiest thing we do, you take the degree, I don't know what letter we're on here, and subtract 1. So f of x is equal to x cubed plus 3x squared minus 5x plus 4. N minus 1, 3 minus 1 equals 2 turning points. Again, it doesn't mean it will have 2 turning points. It could have 2 turning points. And this is, again, where, I don't have to remember that formula because I'm just graphing and count how many times it changes direction. No, not necessarily, because it may not turn that many times. Usually odd degree ones, yeah, it does. But even degrees definitely do not always do that at all. So we've got to remember that formula out of that. Let's say we had f of x is equal to 3x, x minus 5 squared, x plus 4. What's the maximum number of turning points for that? If you don't have that number of how many, your zeros having repeated multiplicities, because remember from Algebra 2, the degree tells you how many answers you should have when you set it equal to 0, right? So if you have a repeated one, then there's not another one to change directions out of that. So here we have an even degree polynomial. That's degree is what? 4. We got 3x times x minus 5 squared. So that's 3x times x squared is an x to the 3rd times another x is x to the 4th. So the degree is 4. So this one has 3 possible turning points. Doesn't necessarily mean that it will have that, but it could have up to 3 turning points. Again, take the degree, subtract 1. Or is the, Derek's question about why does it not have that, necessarily have to know that. It's good to know why it doesn't have the maximum number when you're doing those, but it doesn't necessarily affect much of anything else we do in here. So this is just a n minus 1. Take the degree, subtract 1, you get the maximum number of turning points. All right, now this is everybody's favorite part of this section. No, solving's too easy. Form a polynomial in standard form. It has zeros, 1, -2, and 3. It has a degree of 3. If we're going to form a polynomial in standard form that has those zeros and a degree 3, how do we do that?
So flip the sign, and that's whatever you put.
Okay, so we build the factors that go with those. So the factor for x equaling 1 would be x minus 1, right? And then the factor for x equaling -2 would be x plus 2. And then the factor for x equaling 3 would be x minus 3. So, like Hunter said, flip the sign and make the factor. That's what we're doing there. And then, we're going to multiply that out to build that polynomial in standard form. So this is what we call intercept form, or factored form is what we call it a lot in Algebra 1 and 2. But we're going to multiply it out and put it into standard form. So we're going to multiply that out. Pick a couple to start with. Don't try to do the whole thing at once. How do you eat an elephant? One bite at a time. So pick 2 of them to start with. It doesn't matter if you pick these 2 or these 2. I tend to work in this direction and then distribute the front one last. It doesn't matter. Mathematically, multiplication is commutative, so you can do it in any order you want to. So I just use this order. X times x, x squared. X times -3 is -3x. 2x would be -1x minus 6. And x minus 1. Some of you are faster at this than others. Hopefully we all get a little faster at it as we go through. So here we would multiply x times everybody. That'd be x cubed minus x squared minus 6x. And then we multiply -1 by everybody. So that's -x squared, positive x, and positive 6. And then we add those together. X cubed minus 2x squared minus 5x plus 6. How can you verify that that is the correct polynomial? Largest degree is 3, so there's a checking point. How can we check to see if it had these zeros? You could do that. That's a hard way of doing it. What's the easy way of doing that? Graph it. If we graph this polynomial, what should it do with those points on the x-axis? Should go straight through the x-axis that's those points. So let's do that. Let's graph it just to verify. X cubed minus 2x squared minus 5x plus 6. There's -2. There's +1. There's +3. Those the right ones? Yes. -2, +1, +3. Not likely that you multiplied it all out and got a random polynomial that does the same things as what it's supposed to do. If you made a mistake somewhere, it will show up when you graph it. Okay, so that's easy to do. Let's do one that's a little bit more difficult. Zeros, -3 with a multiplicity of 2, 5 with a degree 3. numbers that we have here.
X plus 3 squared minus x minus 5.
Okay, x plus 3 for the negative 3, because it has a multiplicity of 2, that's where they're getting the squared part. And then x minus 5 for the 5. Okay? And then we're going to multiply that out. So when we're squaring x plus 3, and this is the most common mistake in Algebra 1, and some reason it's a common mistake in Algebra 2, and guess what? It's a common mistake in college algebra as well. When you square x plus 3, it is not x squared plus 9. It is x squared plus 6x plus 9. Now notice I did not start by multiplying out to the right side there because it didn't make sense to do it that way. If you can't do that in your head, write it out. X plus 3 times x plus 3. And x squared plus 3x plus 3x plus 9. And get that, that's where that's coming from. Didn't take me much longer to do it by hand than it did to do it in my head. Okay? And then we're distributing x minus 5 to both of those things. So that'd be x cubed plus 6x squared plus 9x. And then distribute the minus 5. That'd be minus 5x squared minus 30x. And then minus 45. And what I'm doing there is just stacking them up. When it gets larger, stacking them up can keep you from having a problem that's this long and it's hard to find your like terms when it's spread out like that. Stacking always kind of, lines it up for me. So x cubed minus or plus x squared minus 21x minus 45. Degree 3, check. How can we verify it's got the right zeros? Graph it. What do we know it's going to do at negative 3? It's going to bounce off. You're going to touch the x-axis. And it's going to come down and bounce off of it, come up and bounce off of it. Okay. Building a polynomial by multiplying it out. That's everybody's favorite part of it. Okay. It'll say multiplicity of whatever, and that tells you what exponent to put there. Good question. Absolutely. All right, so problems that you could work on are those. They're supposed to call seniors to a meeting right now.
Pardon the interruption. At this time, I need all seniors to report to the cafeteria. All seniors to the cafeteria. This meeting is not